Coalitional game theory is an approach to modeling strategic situations that stands in contrast to what's usually called non-cooperative game theory. And in fact, coalitional game theory is often called cooperative game theory. The names are a little misleading, and I'll get back to that in a moment, but let's first speak about what situations does coalitional game theory try to model. You may recognize these two fine-looking gentlemen. The person on the left is David Cameron, Prime Minister of Britain, and to his right, as we look at it, his left, as they sit, is Nicholas Clegg, his coalitional partner. Now, here are two political rivals who nonetheless come together, and presumably there's a reason. There's something where they can accomplish together that they cannot accomplish alone. In particular, in this case, command a majority in the parliament. And so that's a classical example where a coalition forms. In fact, we usually, when you think about coalition, we think about political parties. But coalitions form not only in politics, they certainly form in business. So the WIND coalition is the coming together of a number of firms in the United States to promote the joint agenda of wind energy, turbines and such. Again, these are companies who are competitors, and nonetheless they feel that together there are things they can do that they can't do alone. For example, lobby government, establish standards, and things of that nature. Now, coalitions aren't always among organizations or parties or firms or heavyweight things. We as individuals routinely come together to accomplish things together, whether it's to enter in marriage or, for example, build a house. When you have a carpenter, an electrician, and a painter that come together, they together can accomplish something that they can't on their own. Now, the mere fact that people come together doesn't mean that their interests are aligned or that they bring the same amount of value to the coalition they've formed. It could be, for example, that the framer of a construction crew is irreplaceable, but electricians are easy to find and one could easily replace, and presumably when they get paid for the house they build, that should be reflected in how they divide the payment. And so there's a competition of both cooperation and competition here, and so for that reason, calling these cooperative games, as the common term is a little misleading. Just as much as non-cooperative game theory is misleading as well, because, for example, if you look at a normal form game, the canonical representation of a non-cooperative game, one can easily describe a completely harmonious situation of so-called team games or common payoff games, where the interests of the agents are completely aligned. So both non-cooperative game theory and coalitional or cooperative game theory model both competition and coordination. The essential difference is the basic modeling unit. In coalitional game theory, the basic modeling unit is the group, the team, and what they can accomplish, and the analysis is based on this basic modeling.
This video is going to define coalitional games and explain what they're used for. So coalitional games, unlike the non-cooperative games that we've talked about so far, don't model individual agents taking actions. Instead, they think about groups of agents acting together. So the idea is going to be that we think about a set of agents and ask about what coalitions could form, what groups of agents could choose to work together. And to do that, we're going to define how well each different group of agents is able to do for itself. Now, in particular, in a coalitional game, we're not going to think about how the agents individually divide work up within the coalition, or how it is that they coordinate with each other in order to form a coalition. We're going to take all of that as given and instead just think about how the coalition does altogether, what kinds of payoffs they're able to achieve. We're going to begin by making an assumption that is called transferable utility. What this assumption means is that it's possible for a coalition to redistribute the value that it's able to achieve arbitrarily among its members. So, for example, if the coalition is paid its value in money, it would be possible to divide up that money and make side payments among the members in any way. In general, what this assumption amounts to is that we'll be able to assign some single value as the payoff to a coalition and trust that it can be arbitrarily divided up among the members. Under this assumption, here's how we can define a coalitional game. A coalitional game has two parts, N and V, where, as in the previous models we've thought about before, N is just a finite set of players, and we'll again index this by I when we want to talk about individual players in the set. And V kind of acts like our utility function for a coalitional game. It says for every subset of the players, S, so for every coalition S that could form, up to and including all of the players in the game, what is the payoff, V of S, that the coalition can achieve? And this, of course, will allow the coalition to divide up among its members. We'll make a normalizing assumption that the value of the empty set is 0. There are two typical questions that we want to ask using coalitional game theory, the two kind of fundamental questions. The first is, which coalition makes sense to form? Which coalition would like to form in this game? And secondly, once we know which coalition will form, how should the coalition divide its payoff amongst all of the people in the coalition? Now, we're not going to spend very much effort thinking about the first question. It's usually going to be the case that the answer is the so-called grand coalition, which means everybody. So usually all of the agents will agree to work together. However, sometimes in order to guarantee that this would be true, we have to be careful about thinking about how the coalition will divide its payoffs among its members. In particular, here's a kind of game that helps us to think about the first question. We say that a coalitional game is super additive if, for all pairs of coalitions S and T, which are both strict subsets of N, if the intersection between these two coalitions is empty, which means these two coalitions involve entirely different sets of agents, then if we make a new coalition S union T that combines these two coalitions together, the value of this larger coalition is at least as big as the sum of the values of the two coalitions independently. So, in other words, if I make a bigger coalition out of two independent coalitions, the value of that bigger coalition is always at least as big as the sum of the values that those two independent coalitions were able to get on their own. This assumption makes sense if it's possible for coalitions to always work without interfering with each other. And this is often an assumption that we make in a coalitional game. Notice that this superadditivity assumption implies that the highest payoff of all, at least the weakly highest payoff of all, is achieved by the grand coalition. So when we're thinking about a superadditive game, it's natural to think that the grand coalition would want to form. So in answer to the first of the questions that I talked about before, we're going to tend to assume that the grand coalition forms, and we're going to focus on this second question of how the coalition ought to divide its payoff. Now, it's reasonable to wonder what I mean when I say how it ought to divide its payoff. That kind of depends on what the coalition is trying to achieve. And we're going to consider two different ways of answering that question. The first is how it ought to divide its payoff if what it's concerned with is fairness. Secondly, we might instead wonder about how it ought to divide its payoff if what it's concerned about is stability, by which we mean everybody would be willing to form the coalition rather than instead forming smaller coalitions because they might be able to achieve higher value for themselves. And we'll look at all of this in the videos that follow.